Hello everyone. Today we're going to go over how to make a UART receiver so we can send values from the computer to our FPGA. So to start off, we have our FPGA here. I'm just going to show you the demonstration. So we have our UART program running, and when we select COM0, we're going to send values from the computer to this wire into the FPGA. So we need to select our baud rate. So let's say we want to send the byte 0x31. Press enter. So if you can look, we have 1 cent and then 3 cents. So that clearly worked. Let's try it again. Select COM0, 9600. Now let's send, I don't know, 5, 3. So, the program, if you don't do the 0x, it changes it. So we sent byte 3, 5. So we have 3, then 5. Let's try another one. Let's do, I don't know, 87. Oh, what am I doing? COM 9600, 87. If we do 87, it's going to do something different. It's going to use the ASCII. It's 57. Okay, so 57 got sent. 7 in the bottom, 5 at the top. So that's correct. So yeah. Now let's go over how the UART works. So to begin, what we just did is we drove the RX line to send serial data to our FPGA into our UART receiver module, which then converted the results and displayed it on the LEDs, and then the done pulse was so short our eyes couldn't see it. So to send a value from the computer to the FPGA, you need to use this format here, where the computer will shift out, it'll shift out a start bit, and then it shifts out the byte you want to send, least significant bit first. Then after that's done, it has 2 bits where it's held high, those are stop bits. Then after that, the computer will send the next value. So let's say we want to send A5. A5 is equal to, A5 is equal to the one that's A. And then 5 is 0, 1, 0, 1. It's 5. Oh wait, no, that's not even A. Wait, is that A? Yeah, this is A, okay. So we're gonna send this byte first, so 1 gets driven here. Then we're going to send this one here, this one here, 0, 0, 0, 0, 1, 0, 1. So we shifted out A5, least significant bit first to do this. Then the UART receiver would then know to process this and display A5 on the LEDs. So we're going to go over how to design this module right here. To do it, it's really quite simple. All you do is you detect when the RX line goes low. You wait T/2 units of time such that you're right in the middle of the first start bit. Then from then onwards, you sample T units of time later, continuously 7 times. So the RX line goes low, you wait T/2 units of time, then you sample T units later once, again, 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 all the way until you've done it for a total of 8 times. Then after that, you wait 2 times. 1, 2, because those are your stop bits. Then once you've sampled these, you display them and insert a dumb pulse, and then you get ready to repeat the process for the next time the Artix lane goes low. So yeah, we have our module here where, let me bring the thing. We're declaring our inputs and outputs. We have a clock. This little tick is the clock, so we have a clock, Rx input, result, and done. We have 2 parameters for the baud rate and frequency. Then on these lines, we just define our internal registers to use for operations, which will be shown later. And here in line 25, we define T. Like, this is how you calculate it. It's just clock rate divided by baud rate. So in our first state, we're gonna be continuously. Our first state 0 is the idle state, where nothing is happening, but we're continuously sampling the Rx line. So we're going to continuously sample. So when Rx goes low, Rx sampled will change to this, and then we'll go to state 1. In state 1, all we're going to do is continuously increment a counter until count is equal to T over 2. Then we know we're at this time, so then we move over to state 2 and reset the counter, so then we can start sampling. So in state 2, that's where the majority of the logic comes into play. So by the time we enter state 2, we are at this unit of time. So we need to count T units of time, such that when the count is equal to T, we're at time S0, so we need to sample. So we count up when the count is equal to T. If index is equal to not equal to 7, we do this. If it's equal to 7, we do this. The index will start off as 0. So we're going to take this path first. Count, get reset to 0. Then we're going to store the current value of Rx. So here, this bit 1 gets stored into bit 0 of Rx, of result internal. Then we increment index to 1 and go into state 2. Then, because we're still in state 2 at time S0, the count counts up until time S1 when count is equal to T. Then here the index is equal to 1 because we incremented it previously with this. So we're still in this state and executing that if statement because the index is 1 at time S1. So then at time S1, we're going to store 0 into bit 1 of result internal, because this is 1 now. The result internal gets 0, because that's what's stored here. And then we're going to increment index, go back to state 2. We're going to continuously count until this time again. Then we're going to store the value of Rx, which is 1, into bit 2 of result internal. And we just keep repeating that process, each time incrementing the index, so then we can store each Rx bit into a different part of result internal, until finally we get to here. When we get to here in the index 7, we want to drive the result. So the result here gets driven. Because previously for these 7, we stored them all in result internal. We use those, and then we use the current value of Rx here. So we shift that out, set everything else to 0, and go to state 3. So in state 3, what all we need to do is just process the stop bits. So we count up T units of time later, 2 more times. Then we then here this time we're gonna go into state 4, where we just quickly assert a done signal to let it know that we're done. So I'm gonna run a test bench now. So from this test bench, we drive Rx, then here serial data gets converted. So the Rx line gets converted into parallel data, and then later, after the second stop bit has been processed, we assert the done pulse. So yeah, and then same thing happens there. Send out 3, 5. So 5 gets shifted out in reverse, then 3. Then we have our first stop bit here. And we have our next stop bit. And in the middle of the last stop bit, we insert our done. So, and also, we go back to state 0. So yeah, this is how you make a UART receiver in pure Verilog. In the next video, we're going to go over how to send a burst of values using a UART receiver, a receiver RAM interface, and a RAM. You already know how to do this one. And the RAM module is very simple, no need to discuss that. But we will go over how to drive this one, how to make this module.